Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're joined by Monika Kress, who's come across to us from San Jose State University. Monika did her undergraduate and graduate work at Rensselaer Polytechnic Institute in central New York. And then she decided to get a little more warm weather and came across to NASA Ames to work with Chris McKay for her postdoc. She also did a postdoc with Don Brownlee up at UW. She is interested in organic molecules and has traveled to Antarctica to collect meteorites. And in the last 2 weeks, two possibly related things have happened in her life. She is now affiliated with the SETI Institute, and she has got tenure at San Jose State University. So in August, she'll be a full assistant professor.
Associate.
Excuse my terminology. She's also associated with the Virtual Planetary Laboratory, and today she's going to talk to us about building habitable planets and the role of carbon and water. So if you'll join me in welcoming Monika.
All right, thanks. I was wondering when my number was going to come up and SETI was going to invite me up to have peanut butter and jelly and give a talk. Didn't take much arm twisting at all. So originally when Adrian asked me to come give a talk, I just published a paper and he sort of just used that title as a stand-in, and that stood in until about a week ago when I said, you know what, I'm just so tired of all that stuff. And I wanted to broaden it out a little bit and talk about the physics and chemistry of planet formation. And I just finished teaching a course on planet formation at San Jose State, and hopefully we'll teach it again in the future at the graduate level. But I'm already stepping on my wire here. It's going to be interesting. I'm not used to being on a short leash. So, I will talk a little bit about my recent results on disk chemistry and its implications for the carbon inventory for habitable planets. But in the meantime, I'd just like to acknowledge the contribution of my collaborators, including Xander Thielens from Leiden University. He was also my PhD thesis advisor. And Michael Frankloch from University of California at Berkeley is our resident expert on the chemistry that I'll be talking about. He's done a lot of the modeling of these same kind of reactions for sooting flames and cleaner burning fuels, that sort of thing. And Vicki Meadows, of course, is the PI of the Virtual Planetary Lab at the University of Washington. And Sean Raymond is our planet formation expert. And he used to be at the University of Colorado and now is at the University of Bordeaux. What a bummer of a move, huh? Poor guy. Anyway, so in my talk, I'll try to give a pretty thorough background on the physical and chemical properties of protoplanetary disks. And the reason that we get so fixated about these disks is that we often see pictures of this in the news. Well, often if you're somebody like me that likes to keep up on the latest astronomy news via the New York Times website or something like that. And so pictures like this often make the news, and it's understood that stars form in these dense molecular clouds, and also the attendant planets, if they have a planetary system around them. The planets form out of this material also. And the cloud core is probably something roughly spherical, but because of the conservation of angular momentum, when that cloud core collapses under its own gravity, what happens is it tends to flatten out into a disk-shaped object. So that's why we get so fixated about these things that we'll call disks. And the problem as far as building a terrestrial planet in these environments is that the disk is hot at the location where the Earth would eventually like to form. So if you found one of these disks and you wanted to watch it for a few million years as planets formed in there, and you just stuck a thermometer at 1 astronomical unit at the location of the Earth, it would be way too hot to have any kind of frozen water. And even organics have kind of a hard time at 500 K. And the disk is probably at least that for a good part of those few million years of its lifetime. And so that presents a real problem. How do we build a planet out of this, at first glance, what looks to be very hot material? You can build a planet there, but it just doesn't have anything worth talking about in terms of the life-giving substances. And so the protoplanetary disks are the gas-rich ones in which giant planets are forming. The giant planets are very rich in hydrogen and helium, so they have to form within that first little brief phase of the disk's lifetime. And after that, your gas and fine dust gets cleared out of the disk. And I'll talk a little bit more about that. And then a later stage of evolution is the debris disk phase, where it's a very gas-poor disk. And this is the time period in which the terrestrial planets are reaching their final size. And during the debris disk phase, the initial disk has been cleared out of gas and fine dust, but what you do have left over are these big boulders barreling around, and I'll talk about the physics behind that. Okay, so just to remind us, the water and organic content of these Earth-like planets are ultimately going to be determined by the composition of the material that's coming in from the interstellar medium and all the attendant processes that it's subjected to as it does so. The physical conditions in the disk, the presence of any kind of ionizing radiation, either from the central star or perhaps from nearby stars. It seems that our own planet, our own solar system, formed in close proximity to massive stars that proceeded to go supernova after the planet formation process had already started. Also, the thermal history of the planetesimals. This is one of the things that I really won't talk very much about today, but there's a lot of interesting work going on in that. And then I'll wrap up with a little bit of the story of the dynamics of the planet formation process. And what I'm showing here in this little cartoon is that we've got a central star here, and it's showing the orbits, roughly of Mercury, Venus, Earth, and Mars. And Earth is in what we would call the habitable zone. It's the range of heliocentric distances in which liquid water would be sort of stable at the surface of that planet. If you're too much closer in, you start looking like Venus. All the water evaporates and is eventually lost from the planet entirely. If you're a little bit too far away, then you're like Mars, and you might have some water ice there, but it's just too cold to really have any kind of water in liquid form at the surface. So the trick is to get the planet building materials into where the habitable zone is, the water and carbon specifically. And we have ample evidence that disks exist, and that really is based on observational data just from the last 10, 15 years or so. These are all Hubble Space Telescope images of little disks around parent stars. In some cases, you can kind of make out the star, but all of them have this sort of a waste where they, have this ring of dusty material that blocks out the starlight. And what you're seeing here, for instance, in this image, is scattered starlight off the dust that's in the vicinity. But you can tell that they all have this flattened pancake of material around them. In this case, it totally obscures the central star.
Where's the lower?
Just probably one that's at a funny angle or something like that. Yeah, we don't really have a whole lot of choice over whether we're looking at these things face on, edge on, or at some weird angle. And in this case, at least we can resolve these things. When you can only resolve the very closest ones, these disks are on the order of 100 astronomical units, and at 100 parsecs, we're talking about arcsecond resolution. So you can get that with Hubble for the closest ones, but if you're a mere mortal with a normal telescope, you're basically just stuck looking at, a point source and trying to figure out what's going on based on these photons that all seem to come from the same place. So as far as techniques for observing disks, the one that I just mentioned was, actually imaging the disks. But the first way that these disks were observed is through the infrared excess around main sequence stars. A star that was perfectly normal, kind of looked like the sun, maybe a bit younger, but had all this infrared radiation coming from it that just didn't really make any sense. Also, you can have an ultraviolet excess due to a star actively accreting material, which is also another process that happens in disks, and this tends to produce a lot of hydrogen alpha emission. You can also get millimeter or submillimeter of emission from really cold dust, dust that's at a few tens of Kelvin maybe. And you'd find that kind of stuff at 10 to 100 astronomical units away, sort of Kuiper belt sort of distances. And you can also see line emission from molecules that have very strong lines like CO and ammonia. And another way to study disks, just to get an idea of how long these things last and some general properties, is to observe clusters, very young star clusters. You can get an age for the cluster that's pretty well. It's hard to tell the age of just one star, but if you look at a cluster, you can do an HR diagram and get a pretty good idea of what the age of the cluster is to, like on the order of 1 million years or so. And then what you can do is to see how many of those have some kind of an infrared excess. And for star clusters that are very young, they find 80 or even more than 80% of these stars have a disk, and some kind of infrared excess, which we interpret as a disk. And then right around 1 million years, that seems to be when everything goes downhill, kind of literally in this plot. And there's a steep drop-off. Somewhere around 2, 3, 4 million years, stars start to lose their disks. And then by 10 to the 7, 10 million years, maybe the occasional disk in these clusters. And so that's telling us something really important about the physics of these disks. What it's telling us is that if you're going to make planets, you better do it quick. You don't have forever to do it, especially the giant planets that rely on the hydrogen and helium that's trapped in the disk and is basically the first thing to be lost. If you want to make terrestrial planets, what you have to do is by a few million years, you need to have boulders, or at least rock-sized objects that don't get blown very easily out of the disk. So little tiny dust particles will be very readily blown out of the disk or spiral into the sun. And so here's sort of a modeler's view of a disk. You've got the star, and it tends to clear out a space right close to the star. There's a gap there. But then you have very hot gas. Everything is in the gas phase. Even the metal oxides and stuff are going to be in the gas phase. And then you have a region where you have some gas and fine dust. And if you go really far out, the disk starts to sort of flare out a little bit, and that's where you start to get water ice condensing out and other volatile ices, and of course all your rocky and metallic material. But your hydrogen and helium and CO and volatiles tend to stay in the gas phase out there. And this picture is just showing us the whole range of angles that we don't really have a choice over how we're viewing these disks. So a lot of things go into making this a really complicated observational problem. But we can start somewhere, and the place to start is to make something called a spectral energy distribution. And what the spectral energy distribution is essentially taking all the different wavelengths of light, even though you can't tell where in the disk they come from, but you just collect them all, figure out what wavelengths they are, and this is kind of like a photon number. It's a flux basically here. So it's kind of like the number of photons that you get at a variety of different wavelengths. And so if in a very simplified model, what a disk is a star that has this very thin sheet of material around it. In this case, we've just done this kind of hokey thing of putting it right up to the surface of the star. But if it did that, and then so it's really hot here and it gets cooler and cooler. If it did that, you'd get your usual stellar blackbody curve, and then but at some point that would trail off, because geometrically speaking, you've got a whole lot more real estate out here. Even though there's not more mass there, the disk is maybe 1% the mass of the sun, but you've got a whole lot of area that's emitting photons. And so you get way more photons out here than you should if it was just a star. And this is just showing how the temperature decreases as a function of radius as you go out in the disk, which is something that you don't really get just looking at a star there. And so modelers can really go crazy with this. And there's a bazillion different free parameters, which is really frustrating. But of course, being a good theorist, you kind of lump them all together and call them one thing, and it's somewhere in between 0 and 1. And hey, you're in business. And so the disk has a temperature distribution that is normalized to 2000 K, but it trails off as you get further out. So R is the distance from the star, and it's in units of stellar radii. And so P is some number that all these various, grain size distribution is actually very important, because that's giving you the total area, and the other grain properties like the just any number of things, the composition, the size, all kinds of stuff gets folded into this little factor. So if you just had a star, you would have this curve. Well, it's yellow up here, but that's because they're all piled on top of each other. This green curve right here would be if you just had a star. And then if you put in a population of grains that are trailing off with temperature as you go further out, what you have is too much stuff radiating at a lower temperature. And so now what we've got is, once this departs from just a black body curve, so for a black body curve, this would be r to the minus 1. If it's minus 0.95, it starts to come away from the black body curve. And as you go from a p of 0.95 to minus 0.75, et cetera, the majority of that effect is caused by just looking at a population of smaller grains. What you can see is that you get a really different spectral energy distribution. The arrangement of your photons, even though you can't tell where in the disk they're coming from, you can tell they all came from this point source, and you can sort of figure out what must be going on. And you can really go crazy with this. And here's our star again here. Here's the red is just the very hokey disk that goes right up to the surface of the star. So it just looks like kind of a really weird black body curve. So notice the definitely much different slope here and here. But if you have a more realistic disk with a gap in there, the disk doesn't go right up to the surface. And maybe there's a planet that scooped out some of the colder material, so you lose some of those photons because there's no stuff there producing it, or there is stuff, but it's all lumped into one big thing that now isn't showing up as well. Because if you take a whole bunch of really small grains and make them one big thing, you have way less area than if you have zillions of small grains. So there's actually a huge amount that you can do with the modeling for these types of objects, even though you can't resolve it. So here's a close-up of some protoplanetary disks in Orion. And so what I wanted to talk about now is to tell you where that disk lifetime of 1 million years comes from. And we toss this number around, and ultimately where it comes from is that the disk, because it comes from this collapsing cloud of gas and dust from the interstellar medium, the disk now has way more angular momentum than it did, angular momentum density of the same angular momentum crammed into a much smaller object. So it's up to the disk to try to dissipate that, either rearrange it or get rid of it entirely. And so the protostellar core that it formed from had 1,000 times more angular momentum total than the solar system has today, most of the angular momentum being in the planets as opposed to the sun's rotation. And that core collapse is going to produce a disk whose angular momentum density, that's little j, so the amount of angular momentum per mass, and that increases with r, which is the distance from the star. And so in order to redistribute and hopefully at some point lose your angular momentum, you need many, many, many trips around the sun. It's much longer than an orbital timescale. And all these things taken together makes a disk that's going to be stable for, on the order of 1 million years. And there's various ways to transport around the angular momentum. We've got the Rayleigh-Taylor instability and the Magneto-rotational instability, and I'll briefly talk about what those are. And there's also a lot of other things that people are doing research on. Winds that come from the disk in a similar kind of way as stellar winds. Magnetic braking, where the magnetic field lines of the star have to be dragged through the surrounding material, and also hydrodynamic turbulence. And these first two guys tend to redistribute the angular momentum, whereas the other two are a little bit better at actually removing it. But I point these out as areas of very active research, especially among theorists who study disks. And the Rayleigh-Taylor instability you are definitely aware of, even if you don't know it. It's basically what you get when you have two different fluids, and there's an interface there. And even though it might be the most calm of liquids, you're still going to get these little tiny density perturbations. It's impossible to have something that's so completely stable. I mean, it would just be such an unlikely arrangement. And as soon as you start to get a little bit of these, they almost look like little fingers projecting down into the liquid below, as soon as one kicks in, then they all kind of start kicking in. And you get this little feedback, and it drives what we call a Rayleigh-Taylor instability, and that's one of the things that may be operating in disks. We do see these in other astrophysical environments. This is an image of the Crab Nebula. What we've got here is a hot wind from the pulsar that's pushing out on the supernova ejecta that came before. And you get this same kind of finger-like projections into the interior of this nebula. Another instability that I'll mention here, although it comes more into play further down the road in disk evolution, is called Kelvin-Helmholtz instability. And that's what you get when you have two different velocities of fluid, one moving, in this case, over the other, and it causes these little fluctuations which then get amplified and can produce really cool-looking clouds. And so you can get sort of the same effect in protoplanetary disks as well. And I just wanted to briefly talk about the magneto-rotational instability. This is what you get when you have a differentially rotating fluid. And even if it has just a very, very small amount of ionization, you can still get this effect in the presence of a weak magnetic field. And it turns out to be really hard to transfer angular momentum outward in a disk without this kind of effect. People have tried everything but, and I'm not surprised they tried everything but, because trying to understand this is really hard. It has a lot of very scary looking equations and stuff. But simply put, what happens is that if you have two parcels of mass that are politely traveling around on a circular orbit, and it's magnetized, so they feel something like a spring between them. We're simplifying it into little cartoon physics here, but basically it's like having a spring. And what happens is that with the slightest little perturbation, that one of them moves just a slight bit inward and the other moves a slight bit outward, what happens is it stretches that spring being the electromagnetic interaction between these two things. And unlike a regular spring that when you tweak it, it'll get it going, and if there's friction, it'll dampen it out, what happens here is it actually makes the problem worse. It actually amplifies the situation. And what happens is that as the inner one moves, or the one that just got tweaked inwards a little bit, it's now feeling a greater force, so it's moving at a greater Keplerian velocity. The one that moved out is now moving slower, and you can kind of see where this is going. It just makes it worse. And so this is ultimately how angular momentum gets transferred from this guy to this guy. So the net effect here is to transfer angular momentum outward. And I just put this on here. The Lorentz force on a moving charge is going to be proportional to, but perpendicular to, the magnetic field. So here the magnetic field in this particular disk would be either into or out of the page. And this is a little movie that I downloaded off the web. I don't know if it's going to work when I'm all plugged in, but let's see if something cool happens. Oh yeah, good. So what's happening is the disk is sitting there, kind of stable, and then at some point you start to really have this effect where the magnetic field actually is taken into consideration here in the MRI. But the disk will stay stable for a relatively long amount of time, and then at some point that's when everything happens. And so disks are going to be supported against collapse by a combination of all these various factors, including turbulence. There must be some kind of turbulence. The origin of it is under investigation. But what it does is it keeps the disk from getting totally flat. Otherwise, your disk wouldn't last for 1,000,000 years. It's got to have some other thing keeping it fluffed up a little bit. Okay, so now I'm going to talk a little bit about the chemistry of disks. And this is the work that I did that I just couldn't bear the thought of talking for a full hour on again. So anyway, one of the big discoveries from the group at NASA Ames, one of their huge contributions, the astrochemistry lab, was to identify polycyclic aromatic hydrocarbons as one of the dominant carbon-containing molecules in interstellar space. And they're found in abundance in all different kinds of interstellar environments. Here I'm showing some infrared emission. There's bands of these in the infrared and even the visible part of the spectrum, and you see it from all different lines of sights through all different kinds of astrophysical environments. They're quite likely in planetary atmospheres. They've been identified in micrometeorites, interplanetary dust particles, and even macroscopic sized meteorites. This particular meteorite right here is ALH 84001, and PAHs were identified in that, but I think the best example of PAHs in meteorites come from the Carbonaceous Chondrites, which are just chock full of these critters. Okay, so I'll talk a little bit about the PAH chemistry. What makes these molecules special is that they have these very strong aromatic bonds in between the carbon. Not just any bond any carbon-carbon bond is going to do this. to be able to absorb an ultraviolet molecule and re-radiate it in the visible or in the infrared. It takes a special bond to do that. And they're thought to be the cause of these very prominent non-thermal emission features. They are thought to form in carbon stars, but it looks like they may also be able to form from the photolysis of ices, perhaps, so possible photochemical pathways. The reaction mechanism that I'll talk to you about today is pretty well understood experimentally, at least in the context of just thermally driven reactions in carbon stars. It basically involves linking acetylene molecules together until the rings close. And so it's fortunate they've been very well studied in the lab because they have all kinds of interesting applications. But what makes them interesting in the solar nebula and disk environment is that they're extremely stable. Even if you put them under temperatures and pressures where they, at equilibrium, they might not want to be pHs anymore, but they have a very long time to survive until they actually do get converted into something else. So they can withstand these oxidizing, reducing conditions, high temperatures, and even ultraviolet radiation. And it's estimated that about 10 to 20% of all carbon is in the form of pHs in the interstellar medium. And this makes it very interesting to me as somebody that wants to know what planets form out of, because they represent the most abundant form of condensable carbon in the terrestrial planet forming region of disks. If you want to build a planet in the habitable zone, you have to form it out of rocks of some kind. Rocks, maybe those rocks contain ice or something like that. But remember, it's hot there. And so you can't take carbon monoxide, which is the most abundant carbon-bearing molecule. You can't take that and put it in a rock. It's just not going to work. So we really rely on these things to be the feedstock for the carbon in the habitable zone. It's the only thing that has a chance, at least in bulk. And so let me tell you a little bit about the carbon in very primitive meteorites. These are meteorites that have been subject to relatively little altering compared to what a lot of meteorites go through when they are in residence on their parent asteroid. What I'm showing you here is a carbonaceous chondrite. I don't know what ultimately it got classified as, but the carbonaceous chondrites contain about 4% carbon by weight, just the bulk. They have about 10% water of hydration, so not ice, but some kind of water in the mineral lattice. And ordinary chondrites, by comparison, only have about 0.25% carbon, and they have not quite 1% of water by weight. So even though we think of ordinary chondrites as being dry, they still have a little bit of water in there. And interestingly, they have roughly the same carbon to water ratio as the carbonaceous chondrites. They just seem to have less of everything. There's other types of carbonaceous chondrites that have less of everything, pretty much, than anybody else. So they actually 0.5% by weight compared to 0.25%, so just a smidge more than the ordinary chondrites. And they have a tiny little bit of water, but the ratio is quite a bit bigger. The carbon to water ratio is about 10 times higher than the other carbonaceous chondrites. And so the meteorites are telling us something about the parent bodies where they came from. We don't have any meteorites from that went into forming the bulk of the Earth itself, but then the ancestite chondrites, they're just kind of weird. They have pretty much no water. Even for a meteorite, they're weird. So the holy grail of meteoritics, and I was just at the meteoroid meeting last week. The holy grail of meteoritics is to relate the meteorites that we have in our collections to the asteroids that we can see in the asteroid belt. And the best we can do, at least until just last year when Peter Jenniskens managed to pick up a meteorite whose parent asteroid was seen with a telescope coming into the atmosphere, and they were able to tell exactly where that thing came from. But most of the time we just find these things on the ground and God only knows where they came from. So what we can do, though, is to take a reflectance spectrum of the meteorite and compare it to the reflectance spectrum of various asteroids. And you can get some very, sort of bulk characteristics of these things. Bulk meaning just sort of general characteristics. You can see whether there's a feature for water or silicate or metal or something like that, keeping in mind that you're looking only at the surface of the asteroid and God only knows what's underneath. So anyway, this is just to tell us that even though there's been great strides and there's a huge amount of research being done in this area, it's really hard to say that this rock came from this position, like 3 astronomical units or something like that. So it's a lot easier said than done. But we can say for reasonably sure that the carbonaceous chondrites are spectroscopically more related to the asteroids that are further out, so more in the outer part of the asteroid belt beyond 3 astronomical units. Here's a NMR spectrum of the carbonaceous material that was extracted from a meteorite. I forget which one. Oh, Murchison, which is one of the famous ones. And you can see that it has this huge peak at this particular wavelength. And what we're seeing here, this peak represents aromatic carbon. We can't tell exactly what molecule it's in. It's in probably some very complex, larger structure. But the bond, what we're looking at is the bonds themselves. And so there's some other types of carbon bonds in here, including things that are in ketones, aldehydes, carboxyl. But aromatic carbon is huge, so there's tons of it there. And we also see evidence for PAHs around other stars, in the disks of other stars, and they look all different. So what we're looking at here, what I want you to focus on is just right around at 3.3 microns where there's a very prominent PAH feature. And so in this particular set of observations, they're comparing all these young stars that have disks and looking at how the pH feature differs from disk to disk. So this was taken as evidence of modification of PAHs in these disks. So not only are they in there, but they're getting cooked up. So the disk is really best thought of not as a thing that just sits there, but as a process that converts interstellar material into planets. Another very interesting set of observations came from Kara Najida, who used they've done some work with Spitzer and also in the submillimeter to look at different molecules in the disk. But what they were able to tell here is, even though they couldn't be picky about where in the disk the photons were coming from, they could tell that the material emitting these photons was very hot, a lot hotter than you typically get way out in the Kuiper belt. So temperatures on the order of 500 to 1,000 Kelvin. And so they were able to identify these spectral features for acetylene, HCN, CO2, and also water, the usual stuff, water and carbon monoxide stuff. We're not really surprised that's there. All these unlabeled features here are water. And so they've kind of highlighted the interesting ones. Also, OH was in very high abundance there as well. And so they interpreted that as coming from the inner region of these disks. And so one of the things that Xander Thielens and Michael Frankloch and I just wrote up was a study of how the pHs behave under disk-like conditions. So at the high temperatures and relatively high pressures in the inner part of, kind of around where the Earth forms. Let's see what happens to these guys. And so we started with kind of the usual stuff, kind of heat up a comet sort of composition. And we also put the pH pyrene, so A4 stands for aromatic with 4 rings, and then A3, A2, A1, et cetera. And so what we're looking at here is how the pyrene just hangs out for a long time. And then just when you start getting close to a million years is sort of the end here, that just starts thinking about falling apart. And then as it does so, it makes these smaller PAHs, the acynaphthene, naphthalene, and a couple of other things on its way to breaking down ultimately to, to acetylene, actually. So acetylene is down here. Acetylene reaches a really high abundance and stays there for quite a while. And so we thought that, gee, well, they were seeing acetylene. I wish I could say this was a prediction, but really it was a, what the heck is that kind of thing. And so when we saw the high abundances of acetylene, we were sort of interpreting it tentatively, but interpreting that as the breakdown of the PAHs. And it tends to occur over roughly million-year timescales. And so to try to pull the model into all these different models I ran into one coherent little picture, what I did was to just run the model to see what the destruction timescale for the PAHs were over the range of possible inner disk conditions. And at 1,000 K, they stick around for not quite a million years. But by the time you get down to 1,500 K, now we're starting to talk much, much shorter timescales, like even on the order of months and weeks. And once it gets really hot, they don't stick around very long at all. And just sort of for entertainment purposes, I looked at what happens if you subject these pHs to just brief pulses of heat. In this case, I just set the temperature to 2,000 degrees and see how long the pHs would stick around. And so the meteorites are full of these things called chondrules, which indicate that the nebular gas was subject to these brief pulses of extreme heating that lasted on the order of minutes or so. And I thought, well, I wonder if that's long enough to destroy the pHs, and it turns out that it isn't really. So these things can actually withstand chondrule-forming shocks. That was the interesting part of that. So this is where we start to really compare our data from the pH chemistry to the conditions we see in disks. And what we're looking at here is a plot of the distance from the sun. So here's the Earth, here's the inner part of the asteroid belt, which is spectroscopically related to ordinary chondrites. A little out of 3 astronomical units is where the carbonaceous chondrites are most closely related to the asteroids. Jupiter is out here at 5 astronomical units. And so I used the disk models from Robbins-Bell and her collaborators. And so she had like snapshots in time of how the temperature changed as a function of distance. So at 10,000 years, you're very, very hot in the inner nebula, and even out at the orbit of Saturn is still pretty hot. And then over time, at 100,000 years, the disk has cooled off so that at 1 astronomical unit, it's 1100 K, something like that, and so on. Now, the meteorites and stuff have to agglomerate into rocks by about 1 million years or so. And so these little arrows indicate the time period that the meteorites should be collecting into these rocks. Otherwise, that material will just get blown away and won't get recorded in what the rocks contain. And I also put just sort of very rough lines on here that shows the condensation temperature of some of the smaller PAHs and the snow line, which is the temperature at which water ice actually condenses out, which is around 170 K-ish. And so you can see that for the carbonaceous chondrites, they're far enough away that it's pretty cold there. They're definitely going to get PAHs, and they probably get pretty close. We could stretch this down a little bit, a few million years. And it'll probably get water too, so it sort of explains our carbonaceous chondrites. And as far as the ordinary chondrites, that's where it's also pretty interesting. There's no way they're getting much water, but they could get a little bit of the PAHs if that stuff was present in the gas, if it hadn't been already cooked at 1,000 degrees for too long. That's the main difference between the chemistry of the carbon and the chemistry of the water. I mean, water, you heat it up, you boil it, gas phase, freeze it out, whatever, it's still H2O. The chemistry is not interesting. With the pHs, it's a one-way street taking you from condensable carbon to volatile carbon that's never going to go in a rock. And so that's the main difference between the chemistry there. And so we sort of concluded that these inner belt objects are going to acquire no water, but if the PAHs are there, they should get a little bit of it. And indeed, we do see a few types of meteorites that have that kind of relationship. Okay, and this just kind of summarizes some of the disk chemistry results. This was where I was going to do a curtain call, depending on how the time is going, but I think I'm okay. So anyway, this stuff is sort of what I just said, but we proposed a soot line, soot being sort of a colloquial term for PAHs, that occurs in the disk approximately at a temperature of 1,000 degrees. And the meteoriticists always like to ask me, what was the temperature of the disk at 1 astronomical unit or 3 or whatever? And I'd say, okay, when? And they're like, ugh, yeah, you theorists, I'm like, well, it's true. You really got to, this thing is cooling off, it's thinning out. These places where things condense out are marching along through the disk. And so I think that the data from meteorites has a lot to offer on what ultimately goes into making a meteorite and what the conditions of the disk were. But it's not as simple as just saying, oh, it was 500 K at 1 AU or something like that. Okay, so for Act 3 here, I'll segue to these debris disks. And debris disks are the phase of the whole life cycle where your original gas and dust has been cleared out. You've expended your few million years, and now what's going on is the stuff that's left over is in fairly decent sized rocks, things that are too big to just get blown out of the solar system by either just solar wind pressure or Poynting-Robertson drag, which causes them to spiral in. And so these disks have been observed. This is the Beta Pictoris disk, if I can remember correctly. And this shows Pluto's orbit to scale. So, I mean, these things are huge compared to what we think of as the solar system. But they definitely have a mature star that you can determine the star's age pretty well. I mean, people will still argue if it's tens of millions of years old, but stellar evolution models can give us good ages, for things 100 million years old and older. Definitely way too old to have primordial gas and dust. Here's an image of Fomalhaut. This is this famous image from Paul Callis. And not only does this thing have a disk, but they also seem to have imaged a planet in here. And the planet corresponds to where the stuff in the disk has been rearranged a little bit due to the planet's gravity. And so here's the incriminating pixels. This thing seems to have moved exactly the amount that it should have moved given its distance from the star. So the whole guilt by association of planets and disks, and especially these debris disks, seems to be pretty secure at this point. So the stages of terrestrial planet formation really go from the protoplanetary disk stuff that I had been talking about. That really, during that period, you have dust that's starting to coagulate into boulder-sized objects. But I would like for somebody to show me how you can make something the size of the Earth by throwing boulders at each other, because boulders just, they don't really stick together no matter how fast you throw them. If you throw them really fast, they shatter. If you throw them slow, they just sort of sit next to each other. So how do you do that? And so when you're just talking about dust, the grains are very well coupled to the gas. They're just sort of blown in the breeze. Once you have boulders, they're, as far as the gas goes, I mean, they will eventually feel the gas drag if you've got a million years. But they're basically obeying the laws of gravity, and they're moving at Keplerian velocities. The gas does not like to move at just a little bit slower than Keplerian velocities, so there's going to be some drag there. So the next stage, which means a whole nother community of astrophysicists, studies the growth from planetesimal-sized things, these boulder-sized things, up to moon-sized, what we call planetary embryos. And what we have here is a large number of gravitationally interacting objects, things the size of the moon. I mean, they're overall obeying the sun's gravity, but when they get close enough to each other, you can bet they start feeling each other's gravity too. Mutual gravity is now going to be important in addition to the star's galaxy, or the star's gravity, and then these planetesimals are going to be colliding and merging. And then the last step is once you have dozens of these moon-sized things clocking into each other, ultimately you're going to wind up with something we've got here today, which is a small number of very massive, widely spaced bodies. And this weak gravitational perturbations are going to lead to that last stage of these giant impacts, these moon-forming events. Sort of impact isn't even, sort of that word is wasted on what's going on there. So to put it sort of in a cartoon format, what we have here is the primordial disk. This is the gas and dust-rich disk, and pretty much you have dust everywhere there's gas. But the particles will eventually settle out. It actually turns out that they will settle out pretty quick. You actually need to fluff it up a little bit to keep it, probably some kind of turbulence doing that. And but definitely what you get is an enhancement over time of the concentration of dust at the midplane. And then the last step here is the formation of big solid chunks, which somehow or other have to stick together. And so a few critical steps here is that, so this is the dust settling out towards the midplane, but then what's happening is that you get this shear, which is going to cause some turbulence. And the shear results from the fact that the gas up here, its orbital velocity around the star is just a little bit less than the Keplerian velocity. These guys here are basically trying to obey gravity. And as a result, you have slow-moving gas sitting on top of faster-moving gas that's being dragged around by the boulders. And so that seems to be a critical step in initiating the formation of these larger objects. And so one thing I wanted to point out, that I didn't really have an appreciation for this until I taught the planet formation class, but even if you started out with all these very well-behaved, nice little rocks all in their little circular orbits that never, clocked into anybody, even if it starts out like that, which it would be totally unlikely that it would, but even given that, the physics of the situation has no choice but to start amplifying the eccentricities and also the inclinations, how far out of the plane of the solar system these things are. And it's just a little perturbation winds up making a huge difference here. And it actually follows a Rayleigh distribution function, and we can think of the x-axis here as either the eccentricity or the inclination, and then this is just sort of a parameter of how eccentric or how many of them have an eccentricity of whatever this is. This is like number of objects with this property with an eccentricity, or, I mean, you can't have an eccentricity of 10 or whatever, but just sort of using this as a parameter. What's happening is that even though you might start out with everything all with the zero eccentricity, over time, what happens is that the distribution will flatten out and make the system dynamically hot, meaning it has a lot of critters with high eccentricities and high inclinations. And the two things put together spell not only collisions, but collisions at high speed. And so what happens is that you have these numerous gravitational encounters that the ultimate effect is to slow down the big guys and speed up the smaller ones. And then the smaller bodies are going to be moving too fast to really respond very well to the gravity of others, or they don't spend as much time in proximity to the big thing. And then the large bodies ultimately are going to grow faster, and you get this process called runaway growth. And here's the results from Sean Raymond's numerical experiments of this process. And what we're starting out here is a whole bunch of objects, all at very well behaved, low eccentricity. And I think these are all comparable in size, like lunar size, or at least hundreds of meter size objects. And so this is at time t equals 0. And the eccentricity is they're basically on circular orbits. And then as time goes on, they start pumping up each other's eccentricities. And not only that, but as you watch here, all the red stuff tends to stay. The color coding is indicating how much water these guys have in them. You get more water in the things that are further away from the sun, and none when you're really close to the sun. And maybe just a little bit in the middle. And as time goes on, these things are not only getting kicked up into more eccentric orbits, but they're also getting shuffled around to different distances from the sun. And so you're actually shuffling in water-rich objects in closer to the sun, much more so than you're shuffling water-poor objects out. And that's basically water runs downhill, and here we go. So at the end, you're left with these couple of big guys, a few small guys too. That could maybe be sort of a remnants of an asteroid belt, or maybe some indication of an asteroid belt. And then you have 3 fairly decent-sized planets here. And they have a fair bit of water in them. And it turns out that Earth and Venus, even though they're at different distances, they probably started out with about the same amount of water. And so that would explain the Earth and Venus pretty well. The reason we call these numerical experiments is that it's basically a random process that's happening. So if you start things out just a little bit differently and hit the start button, then you might get 2 planets here, and maybe, or something like that, or maybe 4 slightly different sizes. But you never get 25 of them hanging out here at 200 million years into the integration. And you almost never get 0. I guess 0 occasionally happens, but it's not, usually you just get like a little handful there. And so the picture, from what we understand at this point, is that this very early on, the trick is to get the dust into something that's not going to be blown out of the solar system in a million years. And once you have those kilometer-sized planetesimals, the standard picture is that you get this runaway growth of kilometer-sized objects, but you could potentially concentrate them through some kind of a turbulent mechanism. So there's these 2 options here, depending on which one you like. And once you get to this phase, this is what we call the oligarchic phase, which it's basically when all the big guys start eating all the small guys, or not letting the small guys get bigger. So the big ones get bigger. It's kind of like the way the banking system works in the United States. And so then this oligarchic phase just leaves you stranded with a couple of big guys that survived the war even better than they were before, just like Goldman Sachs. Okay, so anyway, just to wrap up, because not only am I running low on time here, I actually have a flight at 4 o'clock out of SFO. But so the disks really are best thought of as a process by which interstellar matter is converted into planets, not just a thing that sits there, even though they look like it from the pictures, but they really are a process. There's a lot of physics happening in there, and on timescales that are extremely short compared to our usual astrophysical timescales. And the physics of these disks requires angular momentum to be transported outward in the disk and eventually gotten rid of altogether to leave us the solar system that we have today. And turbulence definitely plays a role to support the disk from having too rapid a collapse, and also turbulence probably also helps in the planet formation process. And then ultimately to get a planet that has the things that we need for life, the water and the carbon, it requires not just a good understanding of the chemistry that's happening in the inner part of the disk. That chemistry tells us what the composition of the individual rocks that go into building the Earth. But also, the physics is going to tell us about how those rocks then get shuffled around. And it's just an incredibly rich area of research right now in astrobiology. And so with that, I'll wrap up, and I'd be happy to take any questions that you might have.
Monika, I have a question. In your models of the PAHs breaking down, do all PAHs break down at the same rate, or if you're a larger PAH, do you break down more slowly?
That's a really good question. There are bottlenecks in the process. It's not that it just politely goes from the 3-ring to the 2-ring to the whatever. We modeled the details of the chemistry starting from the 4-membered ring. And that thing, pyrene, has relatively few hydrogens hanging off the edges. It's more condensed than some of these other pHs, which might be in chains or something like that. Things that are more, if you have your aromatic rings in a chain, then you have all these vulnerable bonds. You have lots of places where a carbon can get attacked. But if you have, it's kind of like the most stable thing is a sphere. So in the case of the PAHs, they're flat. And the ones that are arranged in a more circular orientation, like pyrene, cornene would be the next one up, all those ones are relatively stable compared to their next member down that's already has a ring that got tapped into. And the reason ultimately is that the bonds are a little bit weaker once it's already not a circular shape anymore. So there's bottlenecks as you are breaking them down.
And so they will move into a smaller ring configuration, so smaller rings will then break down progressively.
Right.
Okay.
Right.
We know that there's a lot of large planets very close to the stars from the lambda shift methods, but and you also noted that this process of planet formation is very chaotic. Do you ever see any of the dynamic simulations producing a planet very close to the star, or do you think these are Jupiter-like planets that somehow migrate in from the outer solar system?
It seems to require the formation out where Jupiters normally form, if we can call it that, and then the migration of these things inward. And there's a couple of different ways to migrate inward, as opposed to just forming this thing right there. So not only are we seeing evidence for the little things, the meteorite-sized things getting shuffled around a bit, but there also has to be some planet-sized objects, Jupiter-sized objects that also move around. But as they do so, what they're doing is shuffling the other guys further out, ultimately.
You made some comment, I didn't actually get the full thrust of it, that the PAHs condense before water does and somehow trap it. Did you say something like that, or did?
The PAHs in general have a higher temperature at which they will condense out. And so water has to be at about 170 K, whereas naphthalene, the smallest pH, is somewhere like around room temperature-ish. So the pHs, if you have a gas that cools off all the way down to, say, 100 K, then it'll take everything with it, whatever's there, including the water. But if you have a gas that's at, say, 300, 400 K, and then it gets cleared out before it ever gets lower than that, it might get some of the pHs, but it won't get any of the water. And so what we were looking at is some way to determine whether a meteorite, like if it doesn't have pHs, is that because they were destroyed while still in the gas phase, or was it because the gas was just too hot for the stuff to condense, and that's something that we still have to work out. But it looks like at least in some places in the disk, that these things should have been there. If we see the pHs and no water, then they must have survived and then condensed.
Have you considered the thermal modeling for the interiors of the planets as you get closer being consistent with what we have in our solar system, since we appear to be the only solid planet with a molten core?
Well, the easy way to answer your question is to just say I haven't done any modeling of the interior of planets, but that is a really interesting avenue. I think the modeling of the interior of planets of these icy things that are molten on the inside, to what extent can you maybe destroy the pHs? Maybe they were there, but the thing got so hot through the radioactive heating that they got blown off. And so are they not there because of that, or because they never were, or because it was absent from the gas? That's, it's a complicated problem.
Two questions. One, have you compared some of the turbulence models in the disk to things that you actually see, like around Saturn's disk or planetary disk? And the other question I had was, you mentioned that in some of the simulations you got a 0 result. In that result, where did the mass go in the simulation? Thank you.
Well, that's too bad that Ignacio just took off, because he could have dealt with the first question. And could you just remind me your what the second question was? So around Jupiter and stuff.
The 0 result. Where did the mass go in the simulation with the 0
Oh,
result?
so ultimately, the constraints that we have are the composition of meteorites and understanding their thermal and chemical histories and the extent to which aqueous alteration has played a role. So there's a whole community of people that looks at the chemistry that's happening in these rocks. That's why right now I'm kind of relying on the most primitive solar system material. The chondrites, like the primitive chondrites, are pretty good. The CMs and CIs are they have pretty good constraints on this. The observations of pHs and disks provides another constraint. Looking at primitive organic matter in interplanetary dust particles that are thought to come from comets, that probably is also going to be that would be a good starting material kind of thing to look at. So there's different ways to constrain it, but then it's sort of a convoluted story trying to tie all these things together.
So chemistry, the C2H2 to CO ratio that Karn the G to C, for instance, how does that compare with what you might see in comets, for instance? And is there a clue there in terms of this combustion of pause that you're alluding to?
I think acetylene has been detected in comets, but at very, very low abundances, and it's at very, very low abundance in the interstellar medium. It's got good, rotational spectra, so people have been able to find it, but nowhere near the abundance that they're finding. They're finding it in comparable, like 0.1 compared to CO, which is way more than what you see in the interstellar medium. So there definitely is something interesting there. They're looking at something other than just an evaporated comet.
That's very interesting.
So going back to the pictures of meteorites you showed earlier, and then talking about the carbon to water ratios, is the heating history of the non-carbonaceous chondrite groupings consistent with the carbon to water ratios and the heating, whatever histories you'd imply based on their relative abundances? Or that's something you could check if it hasn't been done.
Yeah, it's kind of hard to say. Definitely all of those meteorites have experienced some kind of thermal metamorphism, and so that's why there is the concern that, gee, this might have gotten in there and then been processed and lost by evaporation. But pHs are kind of hard to evaporate. From my understanding of the chemistry, once they're in sort of a solid material, when you heat them up, they tend to almost link together and make a more and more refractory substance.
They grow essentially.
Yeah. So that might be a process that actually keeps them in some of these meteorites, despite the heating histories.
Okay. I just think it might be kind of a cool, just sort of back of the envelope kind of comparison to make to see if that's in keeping with just basically the oxide condensations temperatures you predict for those meteorites.
Oh, okay. All right. Interesting.
Okay, if we don't have any further questions, I have a
Oh, I got my SETI pin.
yes, a SETI pin. So welcome to the SETI Institute.
Well,
And
thank
if
you.
Join me in thanking Monica.